All right, so let's finish talking about the Sn2 reaction today. And what we just finished talking about in our last lesson was the leaving group ability. And we saw that there is only 5 leaving groups that are acceptable in an Sn2 reaction, and they're shown over here. So just memorize these 5 leaving groups: iodine, bromine, chlorine, water, and the sulfonate leaving group. That RSO3 is called sulfonate. I'll write it out for you so that you know how to spell it. Sulfonate. Okay, so now that we've seen these leaving groups, I want to show you a common student error. I know that you guys like to see errors because that helps you make sure you understand things correctly. If you know where other students make mistakes, that can help you prevent making the same mistake. So let's take a look and see if you can spot the mistake before I even tell you what it is. So let's take a look at this Sn2 reaction and see if you can tell me what's wrong with it. Okay, so there's the alcohol plus sodium cyanide produces Okay, so this is an Sn2 reaction. What's the problem here? What's being substituted here? Well, it looks like the alcohol group is being substituted with the cyanide group. But what's the problem with that? The problem is that OH is not a good leaving group. So this reaction fails. Nothing happens. If you try this reaction, it won't work because OH is not one of our 5 good leaving groups. Remember, our 5 good leaving groups are iodine, bromine, chlorine, water, and sulfonate. OH, hydroxide, is not one of them. In fact, you can see hydroxide is way over here on the bad leaving group side, which is not okay. But there's an issue here. And the reason that students like to make this error is what you'll see, alcohols are very common in organic chemistry. A lot of times we want to do an Sn2 reaction with an alcohol as the starting material, but we can't. So let me show you a workaround. Let me show you a way you can get around this issue. I'm actually going to show you 2 workarounds. Okay. The workaround is, the strategy is the same in both cases. The workaround is to convert OH into a good leaving group. Then do Sn2. Okay, and so there's 2 ways to turn the alcohol into a good leaving group. So I'm going to show you 2 reactions that you can do to turn that alcohol into a good leaving group. The first I'm going to call the old school method. And the reason I call this the old school method is because this is a very old reaction. One of the first organic chemistry reactions ever discovered, actually. So it's going to be called the old school method. And only I call it that. So if you look in a textbook, they have some stupid name for it, you know, halogenation of alcohols or something like that. I like the old school method. Let's stick with that. How does it work? Use HX, where X is a halogen. Where X equals the nucleophile you want to replace the OH with, but it has to be a halogen. So that could be, for example, chlorine, bromine, or iodine. It doesn't work very good with fluorine, so just those 3 halogens. And let me show you how it works. It only works, for now we'll see, it only works with primary alcohols. Remember that a primary alcohol is an alcohol that has only 1 beta carbon, so only 1 carbon attached to the carbon that the alcohol is attached to. And we're going to add HBr, hydrobromic acid, and let's see what happens. The alcohol acts like a base and gets protonated by the strong acid HBr, so we can draw the mechanism for that. The lone pairs on oxygen grab the H, kick electrons onto bromine, and then what we get is protonated alcohol plus Br minus. But look what happened here. This is the magic. By protonating the alcohol in the presence of bromide ion, we've set ourselves up for a perfect Sn2 reaction. Take a look now. Our OH group which was a bad leaving group, is now an OH2 group, water, which is one of our 5 good leaving groups. Remember, H2O is one of our good leaving groups. And what do we have here? OH2, which is H2O. So that means it's a good leaving group. And look what else we have. We have bromide nearby. Bromide is a strong nucleophile. So the lone pairs on bromide will attack the sp3 hybridized carbon attached to the good leaving group and kick out water as a leaving group. And the product is going to be Br. And what's the byproduct? The leaving group, which is water. All right. So this is a cool transformation. You can take a primary alcohol, treat it with HBr, HCl, or HI, and replace the OH with a halogen. Now, this reaction is quite bad. It's bad for a number of reasons. First reason, poor yield. Meaning the conversion is low, so you may not have a very good percent yield. If you remember back from your general chemistry days, percent yield is like how much of the starting material gets converted into the product. So it's poor yields, which means it's not very economical. It only works with primary alcohols. So that sort of limits the utility, that it only, if you took a secondary alcohol, this reaction wouldn't work the same. I'm going to just put in parentheses here for now, because we're actually going to revisit this reaction a little bit later. And another limitation is that the nucleophile that you can replace the OH with is only Cl, Br, and I. So it's limited in a lot of ways. Low yield, primary alcohol only in terms of the substrate, and the nucleophile could only be one of 3 things. So, but, I mean, let's give it a break. This is an old school reaction. It was pretty good for the time, but we have better methods now. So on the next page, I want to show you a better way to do this reaction. And we'll call this the high-tech method. Again, only I call them these things, the high-tech method. The high-tech method involves turning the OH group into a different good leaving group, specifically the sulfonate. So you may have seen that the sulfonate, that RSO3- was one of the good leaving groups. You're probably wondering, well, that's such a random leaving group. Why would that be mentioned? Well, it turns out it's because of this high-tech method. So in this method, we are going to make something called a tosylate. Which is a type of sulfonate, one of our 5 good leaving groups. And then do Sn2 on it. And the nice thing about this reaction is that it works with primary and secondary alcohols. Versus the other method, which only worked for the primary alcohols. In fact, this even works with tertiary alcohols, except that Sn2 doesn't work very good on tertiary substrates. So we're just going to use it on primary and secondary alcohols, but know that it does work on any alcohol. Let's see how this method works. We'll start with our alcohol. And of course, our alcohol, you can't do Sn2 with it because it has a bad OH leaving group. Okay. To that substance, we are going to add a chemical called tosyl chloride, which looks like this. You don't have to memorize the structure of tosyl chloride. I'm just going to show it to you here. It's a sulfonyl chloride. They sell this stuff by the bucket at chemical supply stores, and it's called tosyl. It has a very strong smell to it. It smells kind of like popcorn or something like that. In fact, I had one of my students when I was in grad school. I had a student who worked under me and basically just did chores for me. And it was great because she got to learn chemistry and I got to benefit from her doing chores. And I tried to give her interesting things to do, not just like washing glassware and stuff, but actually doing chemical reactions. But I felt terrible because one of the chemical reactions I gave her involved tosyl chloride, and she had these long bangs that went over her face, and she was always doing like this. And unfortunately, some of the tosyl chloride was on her hand. So when she's moving the bangs out of her face, she got some tosyl chloride on her face, and it caused a terrible burn on her face. So the tosyl chloride is very corrosive. We learned that day. But of course, even though she was wearing gloves, the gloves don't help you if you touch your face with your gloves. So be very careful with tosyl chloride. It smells bad and it burns you. And then in addition to the tosyl chloride, we are going to add some pyridine, which also smells terrible. The structure of pyridine looks like this. It's a 6-membered ring with the nitrogen there. Pyridine's a little messy here. Let me make it look a little better. It's kind of like benzene, but with one of the atoms replaced with a nitrogen. And what this is going to do is it's going to turn the alcohol into the sulfonate. So the sulfonate looks like this. Now, that is really long to draw over and over again. So because it's such a popular substance, the chemists have abbreviated it OTS. So if you see OTS, that is the tosylate. In other words, this little guy, OTS, is this whole thing here. So it's an abbreviation. And this is actually on your abbreviations list. So if there's that handout I gave you earlier in the semester that had the common abbreviations, OTS is actually on there. And the nice thing is that this guy is a good leaving group now. It's one of our 5 good leaving groups. Specifically, it's the sulfonate. The RSO3 minus is a good leaving group. Okay. So let's take a look. Now, you don't have to worry about the mechanism for this reaction. There is a mechanism that converts the OH into the tosylate, but you don't need to know that mechanism. It's too complicated. Don't worry about it. So let's see how this reaction would look in practice. Okay, if we take, say, for example, this chiral alcohol. It's got that wedge there. And if we treat it in step 1 with tosyl chloride, you can abbreviate it TSCl, that's a nice abbreviation, and pyridine, you can abbreviate that PYR period. That's going to turn our OH into the tosylate. So let me just show you what will happen after step 1. It won't affect the stereochemistry. The stereochemistry will stay a wedge, and we'll get OTS here. Now we've converted our alcohol into a good leaving group, the sulfonate. Then in step 2, we can do an Sn2 reaction, so we can add a nucleophile, like, for example, KCN. Now the CN-, which is a strong nucleophile, will attack the carbon attached to the leaving group and kick out the leaving group in an Sn2 reaction. Remember, Sn2 reactions proceed with inversion of stereochemistry. So at the end of the reaction, we'll get this. So this is a really cool process. We started with an alcohol, which we really couldn't do anything with. It didn't have a good leaving group. So in step 1, we converted the alcohol into a tosylate, making it primed to do Sn2. Then in step 2, we added a nucleophile. It could have been anything. In this case, we added KCN. We'll talk about some of the popular nucleophiles in Sn2 reactions, but Cn- is a very popular nucleophile. And the Cn- attacks the carbon attached to the leaving group, ejects that leaving group out, and then we're left with the product, which has inverted stereochemistry. So this is a nice reaction. Except for the toxic chemicals that burn your face, as long as you're careful. It's nice because it works with primary, secondary alcohols. And yes, it works with tertiary alcohols, but they don't do Sn2 very well, so we only talk about primary and secondary alcohols. And because it's a 2-step process, you can use a variety of nucleophiles. So whatever you do in step 2, that's going to be what replaces the tosylate ultimately. So unlike the old school method, it's not just limited to bromine, chlorine, and iodine. You can really use a variety of nucleophiles. So I'll just say many nucleophiles are compatible. And yeah, so this is a nice reaction. It enables us to use alcohols in Sn2 reactions. So anything that does that is a good idea because alcohols are very common. All right, if you remember in the last lesson, this was sort of a detour. I wanted to talk about two more things that affected the rate of the Sn2 reaction, and those were nucleophile strength and solvent. So let's move on there, and we'll say This is C. I can't remember if I was doing letters or numbers for these different things. Let me go back and see. I did numbers. It looks like I was mixing numbers and letters. Okay, we'll just call it part C. Okay. Part C of the things that affect the rate is nucleophile strength. And this is pretty obvious because the better the nucleophile, the better the Sn2 reaction. And when I say better, I mean the faster the Sn2. Okay, so what are some factors that affect nucleophile strength? Well, it's similar factors to the leaving group abilities that we talked about, but kind of opposite. Not completely opposite, but sort of opposite. So the first thing we want to look at is periodic trends. And so if you look at a sample periodic table, it looks kind of like this. The best nucleophiles are going to be down and to the left. So better nucleophiles down here. Okay. For example, NH3 is a better nucleophile than H2O because nitrogen is more to the left than oxygen, and left is better. Similarly, iodine is a better nucleophile than fluoride because iodine is lower on the periodic table than fluoride. So why do these trends exist? Well, horizontally, it has to do with electronegativity and basicity. In other words, you do not want an electronegative nucleophile. If the nucleophile is electronegative, it's going to hold its electrons very closely to it, and it's not going to want to give them, and that's what nucleophiles do. They give electrons. So you don't want the atom to be electronegative, and so that's why as you move to the left, where atoms get more and more electropositive, they become stronger and stronger bases and stronger nucleophiles. So more basic equals better nucleophile. And vertically, it has to do with atomic radius. And the way I remember this is that bigger electron clouds are more nucleophilic. So that's kind of reason number one. Reason number, I guess, two is a property called polarizability. So when you have a big atom, it's more polarizable, meaning that the electron cloud can get like shifted to one side more easily and create a more concentrated negative charge for the nucleophile. So just having a larger... Let me just try and... This is a better way to do an analogy. Let's say you're trying to push something through a keyhole, okay? You've got a tiny little keyhole and you want to push a piece of fruit through the keyhole, okay? What is going to be easier to push through a keyhole? An avocado or a walnut? The avocado is going to be easier to push some of it through the keyhole because it's soft. It can just like get kind of crushed into there. It's a similar idea with polarizability. When you have a big atom, it can kind of be pushed into a small space a little bit better, versus a really small hard atom cannot really be morphed to fit into a keyhole, even though it's technically smaller. Hopefully that analogy kind of makes sense. And then the last reason, larger atoms can't be solvated as readily. Remember, these Sn2 reactions are not occurring in a vacuum. There's solvent molecules all over the place. And so you can imagine a large atom is going to be less hindered by the presence of solvent molecules, which are small in comparison. Think of it like this. Imagine driving down the freeway in a Mini Cooper and hitting another car. Not good. Mini Coopers, they're a very small car, and they're going to get in big trouble when they hit another car. Even a motorcycle, if you hit a motorcycle in a Mini Cooper, that would still be really, really bad for both parties involved. Now imagine though you're driving a huge dump truck. If you hit a Mini Cooper, well, your dump truck is still going to go. You know, it's still going to keep on moving. It's not really going to, you may not even get a scratch. So that's kind of the idea. You can imagine a large atom, when it bumps into solvent molecules, it collides with solvent molecules, it just pushes them out of the way. Versus if you're a really small nucleophile and you hit a solvent molecule, that could really ruin your day. So those are kind of the reasons why large atoms are more nucleophilic. And by the way, I'm going to give you a list of nucleophile strengths, and so you can see some examples of like really, really strong nucleophiles and other examples of like weaker nucleophiles, and see if you can spot the periodic trends in that list. So check out on Canvas that list of nucleophiles. Okay, second thing that can affect nucleophile strength is formal charge. Formal charge. And negatively charged nucleophiles are more strong than neutral nucleophiles, which are more strong than positively charged nucleophiles. So consider the following reactions. You have ethyl chloride plus the hydroxide ion to give ethanol plus Cl minus, versus if you took the same starting material, ethyl chloride plus H2O, to give this protonated alcohol plus Cl minus. Which one of these are going to be faster? It's going to be the top case scenario, because the nucleophile, even though they're both based on oxygen, so periodic trends can't explain the difference in rate, it's strictly based on formal charge. So the hydroxide ion has a negative formal charge, so it's better nucleophile, so the Sn2 reaction is faster. Okay. Last thing to consider for nucleophile strength is sterics. And it turns out that hindered, bulky nucleophiles are worse. So doing an Sn2 reaction is kind of like moving for a new job. Is it easier to get up and move to a new country or a new city to start a new job if you're a single person? Or is it easier to pick up and move and start a new job if you have a whole extended family to take with you? Obviously, it's much easier to do a move if you're single versus you got to move your wife, you got to move your kids, be a nightmare, okay? And the same thing here with this Sn2 reaction. If the nucleophile has a lot of bulk, it has a lot of baggage, it's got a lot of things it's got to carry around with it, it's going to slow down the Sn2 reaction because it can't act like a nucleophile without bringing all of its family along with it. So let's take a look at an example of that. So let's take methyl iodide. This is a very good substrate for Sn2 because it's got low sterics as the substrate, but we're looking now at the sterics of the nucleophile. Okay, let's add methoxide to that, and of course that's going to do an Sn2 reaction to give us this ether plus a byproduct of iodide, but I won't bother showing the iodide byproduct. Compare that to this, so same substrate, methyl iodide, plus now instead of methoxide, let's do a really bulky nucleophile, tert butoxide. So this one's got 3 methyl groups attached to that carbon. And the product is going to be like this. And so the top case is way better because the nucleophile is not bulky. Bottom case is worse because the nucleophile is very bulky. In fact, the tert butoxide nucleophile is so bulky, the only time it works in an Sn2 reaction is with the methyl leaving group substrates, because only these substrates are so good at Sn2, they'll do Sn2 with pretty much anything, even a crappy nucleophile like this, which is way too bulky. If you start making this a primary, even secondary, definitely if you make it a tertiary substrate here, this reaction fails. So I'll even put a little asterisk here. Only time tert butoxide works as a nucleophile is with methyl leaving group, the very best case of electrophile. All right, so those are the three things that affect nucleophile strength. The periodic trends, you want to be down and to the left as much as possible for your nucleophile. Formal charge, you want your nucleophile to be negatively charged if possible. And finally, sterics, you'd like your nucleophile to be sleek like a bullet and not really bulky and have a lot of groups attached to it. All right, last thing I want to mention in terms of rate is the solvent. I talked about the solvent, so let's talk about that. The solvent can have a big effect on the rate of an Sn2 reaction. And we don't really think about the solvent too much, but it's important. So Sn2 reactions, I'll just give you the punchline now, are best in polar aprotic solvents. That's the punchline. So let me just define some terms for solvents, because you're probably wondering, like, what is protic, what is polar, what does all that mean? So 3 key terms. We'll define a polar solvent as the following. A polar solvent is a solvent with a large net dipole. It's kind of arbitrary, but we talked about non-covalent forces and we talked about dipole-dipole interactions. So having a large net dipole means you're a polar solvent. And I've actually uploaded a list of polar solvents to Canvas, so why don't you check out the list and you can see a few of the popular polar solvents. Now there's another term I want to define, which is protic solvent. A protic solvent is a solvent that has at least one hydrogen attached to an electronegative atom. In other words, it's a solvent that can do hydrogen bonding. So it's a protic solvent has at least one H attached to an electronegative atom. And that usually ends up being oxygen, nitrogen, or halogen, I guess. And the third thing would be an aprotic solvent. An aprotic solvent does not have at least one H attached to an electronegative atom. So does not have So it's the opposite of a protic solvent. Let me just show you a few common solvents now, and again, look on Canvas for the full list. So protic. One thing for sure is that protic solvents are always polar. And so two of the most common protic solvents are water. Has oxygen and hydrogen have a bond, so that makes it protic. And also methanol, a very common protic solvent. There's some polar aprotic solvents. These are the ones that are good for Sn2. And so keep your eyes out for these guys. Look for acetone, which looks like this. Look for dimethyl sulfoxide. Looks almost like acetone, but it's got a sulfur in the middle instead. And it's abbreviated DMSO, dimethyl sulfoxide. Another common one is DMF. And another common one is HMPA. You don't have to memorize the structures of these guys, but you should recognize that they are polar aprotic solvents. HMPA is what this one's called. So DMF is dimethylformamide, and HMPA is hexamethyl phosphoramide. hexamethylphosphoramide. DMF is very toxic. I believe it is classified as a reproductive toxin, so really kind of scary thing. If you ever plan to have kids, the DMF is really bad for that because it damages your reproductive organs. So you just breathe it in and it can it can hurt your eggs or it can hurt your sperm production. So definitely avoid DMF if you plan on having kids. Not good stuff. HMPA is even worse than DMF. It is a carcinogen, so it's believed to cause cancer when you're exposed to it at a very high rate. So for these reasons, these two solvents are usually phased out in favor of these two guys, acetone and DMSO, who are a little more harmless. But HMPA, unfortunately, is one of the best solvents for Sn2. Oh well. And then there's some nonpolar solvents. Nonpolar solvents include benzene, hexane, and carbon tetrachloride, benzene, carcinogen, hexane, neurotoxin, carbon tetrachloride. I know this compound, they say it's bad, but I look it up and I'm like, what exactly is it supposedly so bad about it? At first people said that it's like bad for the environment, but it turns out it degrades pretty nicely in the soil. So typically compounds that are bad for the environment are those compounds that just sort of persist in the soil for millennia. So I don't know. I think carbon tetrachloride is really not so bad. It's very expensive though. But regardless, the good solvents for Sn2 are right here in the middle. So these are not good for Sn2, and neither are the protic solvents. Okay, why? So now the last thing we need to answer is why. So first we'll answer the question, why polar? Why is polar good? Polar is good because Sn2 has a polar transition state. We'll talk about transition states a little bit later. I already showed the transition state for Sn2 in the previous lesson. And polar solvents stabilize a polar transition state. So if you can stabilize the transition state, you lower the overall activation energy of a reaction. And if you remember back from Chem 2, was it 102? If you lower the activation energy of a reaction, that is going to increase the rate of the reaction. That's typically how catalysts work. So in this sense, the solvent is in a way acting like a catalyst by lowering that activation energy by stabilizing the transition state. Also, a more practical thing, most nucleophiles are polar. So insoluble in nonpolar solvents. It's important when you do a chemical reaction that everything is soluble. So if any of the ingredients are not soluble, they won't be able to mix properly and the reaction will start taking a very long time. So for that reason, since the nucleophiles are typically polar, polar solvents are typically good. Why are nucleophiles typically polar? Because they usually have like a negative charge or like a lot of lone pairs or polar bonds inside. So if you go back and look at a lot of the nucleophiles we've looked at for Sn2, they're almost all polar. Okay, why is it so important for it to be aprotic? Why don't you want hydrogen bonding? Because protic solvents lower the reactivity of the nucleophile. By hydrogen bonding it. Let me just draw a little picture to illustrate this. Let's say we're doing an Sn2 reaction and our nucleophile is hydroxide. Very potent and strong nucleophile, OH-. Now, if you look at the OH- and you put it in a protic solvent, something like methanol, for example. I'll just draw little methanol molecules around it. The methanol molecules are going to gather around and be like, oh, hello, Mr. Nucleophile. Look what we have, hydrogen bonds for you. And so the hydrogens, the protic hydrogens on the solvent, are going to hydrogen bond to the delta negative oxygen of the nucleophile. So remember, the oxygen is delta negative and the hydrogens are delta plus. So there's a hydrogen bonding interaction between the nucleophile and the solvent. And that's bad. Now the nucleophile is being webbed down by all these solvent molecules and it can't really move. It's being held down like a bunch of little spider webs grabbing onto it. So that's bad. It's going to slow down the reaction. So this picture is showing the nucleophile reactivity attenuated. Attenuated means reduced by protic solvent. So we really want the best of both worlds. We want polar to dissolve the transition state and also to dissolve the nucleophile, but we don't want protic, because protic would start webbing it down with all of these hydrogen bonds and make our nucleophile super weak and not able to do the reaction efficiently. But if we do polar and aprotic, it dissolves our materials and it doesn't do hydrogen bonding, so it's the best of both worlds. Okay, so just remember, polar aprotic solvents, very good for Sn2. And I just want to give you one final miscellaneous fact about Sn2. And let me show you a reversible Sn2 reaction. Let's say we took this propyl chloride and we reacted it with sodium iodide. That's going to replace the chlorine with an iodine, and we'll have a byproduct of sodium chloride. Okay. So if you look at this reaction, it's actually reversible because it can go in the forward direction if I minus attacks the alpha carbon, kicking out the leaving group, but it can also go in the reverse direction if Cl minus attacks the attacks the alpha carbon and kicks out iodide as a leaving group. And this is true because iodide and halogens, and specifically, are both good nucleophiles and good leaving groups. So if you do a reaction like this, it's going to shuffle back and forth between starting materials and products, and it's never going to finish. It's just going to keep going back and forth and back and forth. So this is a reversible reaction. And so it'll exist in some sort of equilibrium will be reached, where there'll be a certain amount of starting material and a certain amount of product, and that'll be what it is. Now, oftentimes we would like to push these sort of reactions to one direction, and we can do that using Le Chatelier's principle. I know you guys know what Le Chatelier's principle is. It's when you can push an equilibrium in one direction. So we can push this reversible reaction towards the heavier carbon-halogen bond. And the way you do this is if the solvent is acetone. So the trick is to use specifically acetone as the solvent. And let me show you what happens here. So we'll take our propyl chloride and we'll add sodium iodide. And we'll do the reaction in acetone solvent. We'll get the same product, the propyl iodide plus NaCl. Well, it turns out that NaCl is not soluble in acetone, so it precipitates out as a solid. And that drives Le Chatelier's principle. So as you start to make the NaCl, it's being removed from the reaction. One of the products is being removed from the reaction by the fact that it's not soluble in the solvent. So it falls to the bottom of the container and is no longer present in the reaction medium. So that actually drives Le Chatelier's principle towards the product. Remember, one of the ways to drive a reaction towards the products is by removing one of the products as it's generated. And the difference in solubility between sodium iodide and sodium chloride is what we're exploiting here to drive the reaction in one direction and stop it from being reversible. Now it'll go towards the product and stay there. And this works for a variety of conversions, as long as you want to go to the heavier carbon-halogen bond. So it works for CCl to CBr. It works for CCl to Ci. That's what we just did now, turn a chloride into an iodide. And it works for turning a bromide into an iodide as well. So as long as you want to go in the heavier direction, from chloride to bromide, from bromide to iodide, or from chloride all the way to iodide, this reaction will work. Okay? So that's a cool little trick using one of the solvents, acetone, for it, which is good for an Sn2 reaction anyway because it's a polar aprotic solvent. So this is a cool little trick that I'd like you to remember. All right, so that's all you need to know about the Sn2 reaction. We know now what are the 4 factors that affect the rate of Sn2. We know about the leaving group ability. We know about the substrate sterics. We know about the nucleophile strength, and we know now about the solvent effects. We also learned 2 little cool reactions along the way, the old school method and the high-tech method, which are going to allow us to use alcohols in Sn2 reactions despite the fact that OH is not a good leaving group. Okay, so that's it for the Sn2 reaction, and next time we're going to start talking about another reaction called the E2 reaction. So stay tuned for the E2 reaction.